I think I'll skip some of the last theorems. They're a bit abstruse, and they don't really introduce anything new. Also, I need to consider the time. The number of pages in this chapter is pretty well double what the number in the earlier chapters. So this is turning out to be quite a long lecture with many parts. Okay, so I'll do the second part of Theorem 17 from the textbook. The first part is about infinite sets, but really this course is about finite group theory, so concentrate on the finite groups. Okay, so here's the setup. You're given an element that belongs to a group, so X belongs to G. You're told that the order of the element, not the order of the group, the order of the element is K, okay? So therefore X to the K is E. You're given a big integer, big N, that belongs to the integers, and you're told, well, here's what you have to prove, that X to the big N equals E if and only if, if, so we have to prove it both ways. I've done this several times now, so I assume you're fairly familiar with how to go about this. So, so X to the big N is equal to the unit if and only if little n, sorry, K I think, sorry, this should be n, little n, okay, little n. So little n is the order, and big N is just an integer. So so X to the big N is the unit if and only if the order of X of this element is if little n divides this big N. So we have to prove it both ways, right? Well, let's do the if case. So call, as usual, call this statement P, call this statement Q. Now in the if case, so P if Q. So if Q is true, P is true. So in other words, we're doing this. So we're going from Q to P. So we're going from so that's pretty typical of if and only ifs. So the convention is start with the if. It's a pretty strong convention in pure math. So start with this and prove that. Okay, so so we start with Q. Now what is Q? N divides, that's what digs means. That's my shorthand for little n divides big N. So N divs big N. That means that you can rewrite N as, how are we? K? Nice. Yeah. Okay, so we can rewrite big N as K little n, right? Because n divides big N, so that means n is a factor, little n is a factor of this, so you can rewrite K of that form. Alright, now we have to prove that X to the big N is E. So let's calculate what X to the big N is, and we'll try to show that it's equal to E. So in other words, prove P, prove the left-hand side. Alright, well we know what n is, it's just Kn, so plug this in, so you get e to the Kn, and that's the same thing as e to the nk, right? And that's the same thing as e to the n to the k, because these are just the exponents, right? But e to the n is, sorry, these are x's, this should be x's, okay? Now x to the n is e, right? Because n is the order of that element. So this is just e. So this is just e to the k. Now e k times is still just e, right? So that's just e. So in other words, x to the n is e. So that's the proof of the if case. Now the other way round, how to do that? Now the only if case. How to do that? So now the only if. So P is true only if Q. So the only way you can get P is if Q is true. So if you do have P, you know you must have had Q. So if P, then Q. So only if is this way. P, then Q. If P, then Q. So, so you start with the left-hand side and you have to prove the right-hand side. So, how to do that? Well, let's see. So, we start with this and we have to prove that. So, well, let's use the division algorithm from the previous lecture. So we'll assume n is bigger than little n. So we'll use the division algorithm. So we'll write big N in terms of little n. That's from previous lecture, the division algorithm. So big N we can write in this form. So some integer, little n, plus the remainder. Okay. Now the remainder will be less than little n and greater or equal to 0. Right? That's what the division algorithm says. All right. So let's calculate. Now we know that x to the n. We know the left-hand side, right? So x to the n is x to this, and we know that's equal to e. So let's do that. So x to the n we can rewrite as, now we use this here. So it's q to the n plus r, okay? And we know that that's equal to e because that's the left-hand side. Right. Well, we can rearrange this. So this is the same as x to the qn times x to the r. Right? So this is the same as x to the n to power q times x to the r. Now x to the n here is the unit because this little n is the order of the element. Okay, so this is just e. So this is just e to the q, x to the r. Right? Now e to the q is just e, x to the r, which is just x to the r. And you're told that that is e. Right? This is e. This is e. Now I've rubbed it out, but any element to the 0th power is e, okay, by definition. So if you can rewrite e as x to the 0, right? So that means r is 0. That implies r is 0. Okay. Now go back here. If r is 0, if that disappears, that means that big N can be divided by n. Right? That means little n is a factor of big N. So, so this then implies that little n divs or divides big N. You see it here. Big N is just q little n. So little n is a factor of that. Little n divides big N here, and that's what you have to prove. That's q. Okay, so that's done. Yeah, I think I'll stop there, and the next portion of this very long lecture, because it's a critically important lecture because it's the basis of group theory, and in the text, the number of pages in this chapter is pretty well double what it has been in the previous chapters. So a long lecture. Okay, so I'll stop, and then we'll do some exercises.